All right, so we have our second test on Wednesday. All right? And that's just the way it kind of lands for you guys, right? So how are y'all doing? Did y'all spend the weekend getting caught up? And yeah?
I'm going to take vacation tomorrow.
Okay. All right, well, today we're going to continue with where we left off, which was the related rates. We did finish the problem with the plane flying overhead, and we were trying to find the rate at which the angle was changing. All right, so the next one on our list, and we're going to try and do this one without the picture, is a street light that is mounted on the top of a 20-foot pole. You've got a man that's walking away from the pole at a speed of 7 feet per second. We want to know how fast his shadow is moving along the ground relative to the pole when he's 12 feet from the pole. So that's what you would be given on the test. No pictures, no diagrams, just there it is. So what are we going to start with?
Oh, we can use, we're going to
Use the
You can draw your own picture.
Start with a 20-foot pole.
Okay, so I'm going to draw you want to start with the instant in time first? Okay, I have a 20-foot pole. Doesn't matter which side you draw the pole on, I'm going to put it over here. And I put a little light on top of it. There's my light. Here's the ground. And this is 20 feet from here to here, right? Yay. We have a man that is 6 foot tall, right? He's walking away from the pole. And at the instant in time that we're talking about, how far is he from the pole? 12 feet. Y'all got that? So I'm going to draw this guy here, 6 foot. He has no arms or legs. He's just a torso and a head. And he is 12 feet from the pole. This was 20 feet. Anything else? The fact, oh, I forgot to put he's 6 feet. Yes, that is definitely relevant.
He's walking away from the pole at 7 feet per second.
Yes. Now, should I label that on this picture? Why not?
Because then you're stopping.
Then I'm stopping him. So I should do the 7 feet per second on the next picture, the general picture. Now let me try and draw the same thing happened the other day. I didn't have any colored markers. Okay, I'll go grab some. The shadow, the light comes out and the shadow is going to be cast on the ground like this. Like here's his shadow on the ground. You know what? I'll give him legs and arms. So his shadow's on the ground like that, right? It's a pretty good shadow, huh?
Realistic.
Very realistic. All right, so there's what we want to know is how fast his shadow is moving along the ground relative to the pole. That's very important. The relative to the pole is very important in the problem. So let's just imagine that his shadow, the tip of his shadow is right here, right? I'm going to put that as like a point. I want to know how fast that point's moving along the ground relative to the pole, which means relative to this point right here. Understand? So there it is. For now, I think that's all I want to draw. Let me draw a general picture. Same pole, 20 foot tall, that doesn't change, right? Same person, 6 feet tall, that doesn't change, right? But what's different here? He's moving, right? So when we draw his shadow on the ground here, right? When we draw a shadow on the ground, he is moving. So the distance from here to him, right? Right there, cannot be 12. So we need to call it something. X, let's call it X, all right? X is that distance. Agreed? And what we're interested in is how fast this point's moving relative to the pole. So let's label that with a variable. That okay? Because it's moving, isn't it? That distance from the shadow to the pole, that's changing. So let's give it some value. Not a specific one, but a letter. So what would you like?
J.
J? I'll use J. Now normally I wouldn't, and only because of the fact that in physics we use I hat, J hat, K hat. And so normally we just don't even mess with J in math unless we're using it for an index and a summation. Sometimes a summation we'll use a J equals 1 to like infinity. I'm just telling you this so FYI. All right, but I'll use J because you are allowed to use whatever letter you want. So J. Got it? Understand? All right, let's try and write down some things that we are given. The things that we want. So what are we given here? 7 feet per second. Now that's a speed, isn't it? We talked about this last class. When you see feet per second, you should be thinking derivative. It's the rate of change of what, though, in our picture of x. Agreed? 7 feet per second is how fast the man is moving, which is really how fast that point is moving along the ground. So I'm going to put what? dx dt 7 feet per second, right? What do I want to know? dj dt is what I want to know. When do I want to know that? When x is 12 feet. Make sense? And I believe that's all I need. Are there any questions on this setup? What am I going to come up with next? The equation, right? I need an equation now. And my equation is going to connect what two things together here? X and J, right? X and J. So any equation you can come up with. Are we allowed to look over here?
Yeah. We're allowed to look over there,
Yes, you can look there, yes. You can look, but then look here. After you look there, look here. Why can we not fix things here, right? Why can't we? Can't stop it from moving, right? We must be looking at this picture here when we try and come up with our equation. So do y'all see anything here?
J minus x.
J minus x is what?
Or squared plus j squared equals.
So you're thinking Pythagorean, like a squared or b squared is c squared? We could. We just don't have this. We don't have this length, right? So Bailey, right? Okay, Bailey's saying j squared plus 20 squared equals this squared, but we hadn't even put a letter here, right? That's correct. If we add a letter, we could do that. So let's just keep that in mind. We could do that. Anything else you see? There are two triangles. You can look at a big triangle and a small triangle. Let me draw that. Formula what?
I'm just remembering this from my pre-calc class. So we use these two triangles and figure out the length.
Yeah, you might be able to do that. Let's see. What is the big triangle, this outside one? I can put 20 here, and then I can put what? J. And then what would the small triangle, which would be the man right here in his shadow, 6 and J minus x. Wouldn't it be? This is J. This is x, so that is J minus x. Understand that, everyone? Okay, there's J minus x. Great, okay. But does that help? I'm trying to come up with a formula that relates x to J. What can you do there? You think about it. I'm going to go grab a couple of colored markers out of a different room. Y'all can think about what you might want to do. Hey, what's up, Ramiro? How you doing? Good, man. Did you have a good weekend?
Yes, sir.
Yeah? How's things going good?
Yeah.
Yeah? Okay, I'll catch up with you. Hey, what's up? Come on. Is your teacher here? Oh, okay. Okay, I'm going to steal 2 markers. I didn't do that. I was never here. Okay. What did y'all come up with? Anything?
20 over 6 equals j over j minus x.
So what are you using there?
I forget what it's called, but it's how you use the ratio between the two.
Good, good. Okay, so look, you have to realize that these 2 triangles are what we call similar triangles. Since they both have this same angle, don't they? So I can say that this angle here is the same as this angle. And if they both have a 90-degree angle in them, then that last angle must be the same, right? So this angle here, does this look familiar to you, these little arcs with the little slashes through them to kind of show you that they're the same? Congruent, equal, yeah. So what we have here are similar triangles. Any triangles that have the same angles are called similar. And there's something called, well, it's not really called anything. It's a result of similar triangles, and this is what it is. If you have 2 similar triangles, the ratio of corresponding sides must be equivalent. Ratio of corresponding sides. What does that mean? That means if I take this side, which is kind of this shorter side here, and I divide it by this shorter side, so 20 divided by 6, that must be equal to this longer side divided by this longer side, j over j minus x. That's what it means to be similar triangles. But you didn't have to do it that way. You could have done 6 over 20 is equal to j minus x over j. All right? You could have also said 20 over j must be equal to 6 over j minus x. Corresponding side ratios must be equal. Got it? So I'm actually not going to use this one. I'm going to think about what I'm trying to do. I'm trying to come up with an equation that relates j and x together. I'd like for my j's and x's to be in the numerator if at all possible. So when I set up my ratio, I'm going to do this. J over 20, okay, I can do that. J over 20 must equal what? J minus x over 6.
What's the significance of having it in the numerator?
I'm going to take a derivative, right, at some point. And if I have my variables in the denominator, I'm going to have to deal with that, right? It might involve quotient rule. I might have to pop them up as negative powers, right? It can still be done. It's just a little easier if I deal with them like this. Understand?
So you want it's easier for the variables or whatever to be.
Yes. Now you can't always do it, but if you're thinking ahead a little bit, you're like, all right, when I come up with my equation, I'm going to take derivative. I prefer it to look as nice as possible. I know this may still look bad to you because you still see division, but just let me write down one more thing, and I think you'll see what I mean. So let's rewrite this, and let's see if I can convince you of this first. I guess I'll do that. J 1/20th j equals 1/6 j minus 1/6 x. Is that the same? Do you see where I'm headed? I'm just trying to get everything cleaned up before I actually put down my equation. All I did was rewrote that, split this fraction into 2, right? 2 terms on top, 1 on the bottom. And now, I want to clear the fractions. I don't know about you, but I'd prefer to not have any fractions. So if you have an equation, can you multiply both sides by something that, I want the denominator to go away. So can anyone think of a common multiple of 20 and 6? A common multiple, not divisor. 60? 60? Everyone agree? 60 is a common multiple of 20 and 6? So what would happen if I multiply the left side of this equation by 60 and the right side of this equation by 60? By the way, this step's not necessary, okay? I'm doing it because I want my math to be cleaner. I want my numbers to be nicer. So 3j equals this, what do you get there? 60 divided by 6 is 10? 10j minus 10x. See, that's a little bit nicer to work with in my opinion. And let me get all my j's on one side and all my x's on the other. How about this? This all right with you? I move my j's to the right. I move my x's to the left. Do I have an equation that relates x and j together?
Yes.
Yes. And that's a pretty clean version of it, isn't it? So that's my equation. 10x equals 7j. So this was all scratch work. What do you do at this point? Differentiate with respect to time, right? So it's time for implicit differentiation. I'm going to do implicit. That means I'm taking derivative with respect to time of this thing. So what is the derivative of the left side with respect to time?
Wait, which one are we using to take the derivative?
This one right here. This equation.
Was it 10 dx dt?
10 dx dt.
Okay, so you're using the dx dt. Okay.
Yes, I'm differentiating with respect to time. So 10 dx dt, the 10 just came along, right? And then I took the derivative of x with respect to time, which is just dx dt. That must equal, the 7's just going to come along, and then the derivative of j with respect to t, which is dj dt, right? And now if you look back on what we have and look back over here, dx dt we have, right? dj dt is what we want, right? So I have everything I need to answer the question. So let's get the solution.
Could we just plug in the 7 for dx dt?
What's that?
You see how you have the dx dt?
Uh-huh.
Since we know that's 7, are we just going to multiply?
Yeah, that's all we're going to do. We're just going to replace that with 7 now. So we have 10 times 7 equals 7 times dj dt. And divide both sides by 7, right? Get rid of the 7's, and you have dj dt is 10. Yeah, and now we have to figure out what the units are. So if you look back at our picture, j was the distance from the pole to the shadow, wasn't it? That's measured in feet. Time was in seconds, you can tell because of here. So our answer here should be what? Feet per second. That's the answer. Now I'm really hoping that someone might point something out here that happened in this problem that really hasn't happened up until this problem.
You didn't have to solve for another variable.
We didn't have to solve for another variable like we did last class.
Like solving the initial equation for a different variable.
Yeah, we didn't need that. I agree. We didn't have to do that here, but there's also something else. Look at our given information, what we want. There's something in there that we didn't use?
You didn't use x equals 12.
We never used x is 12. Did we? Ever. In the problem. Do you agree? Why? Well,
Because
did we mess up?
we used the two triangles,
Yeah?
and one of those was when x is 12, right?
No, we never used
Then I
it.
guess we just got lucky.
No, there's something else. It's not luck, it's telling us something.
That it's constant. Like it's the same forever.
That's right. This is telling us, if you go back and you look at this formula right here, to know dj dt, the only thing you need to know is what? How fast he's moving, right? It's independent of where he is. If where he was mattered, this formula would have an x in it. But it doesn't matter. And this is one of those problems where if we don't do the math, okay, the answer is 10 feet per second, right? if we don't do the math, if we just look at this physical problem right now, I'm going to bring it up here. We're going to take a look. I'm going to do the animation and play it for you. We're going to let this man move across the screen at whatever it was, 7 feet per second. All right. Okay, so if I let this man move across the screen, if we just started this problem right now, and I asked you, is his shadow moving? Is it moving away? Is it going faster and faster as he goes? Is it slowing down as he goes? What would you say? Do you have an instinct answer? I mean, you know the answer.
It looks like it's speeding.
It looks, I mean, think about it. The further he goes away, the further out that shadow has to get, right? So a lot of people would have an instinct that would tell them, look, the further he goes, the faster his shadow has to move away from him. That would be a natural, I think, instinctual response to the question. But we have just shown mathematically that it is independent of where he is. He is moving at a constant rate, right? But so is his shadow. Even though it's further away from him, as he goes, the shadow is moving how fast? 10 feet per second, all the time. All the time. Make sense? To me, this is one of the more profound things that we do in a course like this, because there are times in real-world applications where your gut instinct tells you one thing, but the math proves you're wrong. And you don't want to go on gut instinct when you're building bridges or planes, or, you don't want to be like, yeah, that's strong enough, Sure, that'll hold. I mean, you have to know for sure, and that's why the math is important. We have to have something that settles it for us. All right. Another classic problem. By the way, all these problems I'm giving you are classic problems, all right? Someone takes Cal 1, they'll talk about the cone and the water being poured in the cone. Everyone knows what I'm saying when you take Cal 1. All right, a conical cup is 4 inches tall and 6 inches wide. So I'm gonna treat this problem like it's brand new. I'm gonna draw instant here, general here. I have cone. It's a conical cup. You've seen these, like, they have them next to the igloo. Little coolers, you pull them out and you fill them up with water, right? There's my conical cup. I know that it is 4 inches tall and 6 inches wide. Oops, I didn't really draw this very good. 4 inches, 6 inches wide. It's supposed to be wider than it is tall. My picture doesn't look like it, right? Water is being poured into the cup at a constant rate of 2 pi cubic inches per second. So you've got someone pouring water into this, and water starts coming up, right? How fast is the water level rising when the water is 1 inch from the top of the cup?
About 3 inches.
Yeah, so let me draw my instant in time here. My water level is coming up. I want to know how fast it's rising when it's 1 inch from the top, which means that the water level is somewhere around here. Close enough? That good enough for you? And then let me label that. That is 1 inch from the top, which means it is 3 inches high. That's the instant in time. With me? In general, can I still label this 4 and 6? Yeah, that doesn't change. The cup's the cup, right? So this is still 4 inches. This is still 6 inches. And now my water level, can I put that at 3 inches? No, it's changing, right? So this is where I have to come in here, and I have to put the water level in here. And just remember that that water level from here to here is not fixed in the general picture. This is going up, right? This water level is coming up. So what do you want to call it? Y? Okay. You could call it Y. You could call it J if you want. You could call it W for water. You could call it H for height. So see, you do have choices.
It's the only thing we have a choice of in life right now.
So we have to cherish them. Choices we're given.
So what we know is that y, y is always constant, so it'll be dy dt, right?
I don't know. Hold on. Let me finish writing this down. You know that what?
What I know is that y is always constant and right, so that'll be dy dt. That we want to know how much water is going to be risen up, right? How fast the water is rising.
You want to know how fast the water is rising?
Yeah, that's
Yes.
what the question says.
So what is that?
That'll be dy dt.
dy dt, right? That's what we want. That's what you don't know, right? You don't know how fast that water's coming up, but that's what we want to know. We want to know that what? At
1 inch from the top.
at what's 1 inch? Huh? Yeah, at what 3 inches?
3 inches height.
Yes, but what variable? Y, right? At y equals 3. From our picture, y is the measurement of the height. 1 inch from the top meant that y was 3. Agreed? Okay, what are you given though?
You're given the rate at which it's filling up.
The rate at which it's filling up. 2 pi cubic inches. When we talk about units, that's volume, isn't it? 2 pi cubic inches per second is a measurement of the rate of change, the derivative, of the volume. So this should be dV dt, we call it dV dt. V for volume, right? Is 2 pi cubic inches per second. Everyone still good?
And just to clarify, when you write the d whatever over dt, what is that saying? Just to clarify.
It's the rate of change of that variable with respect to time. So it's the speed at which that variable is changing
Okay.
at any point in time. In this case, this is constant. It's always changing at the same rate. The height, this y, is it always changing at the same rate?
No.
No. Initially, it fills up very fast, and then it gets slower when you get to the top because the cup spreads out. So how fast this changes should depend on how high we are, right? Think about what I just said. The shadow problem, how fast the shadow was moving, did not depend on where we were. This height, the speed at which it's coming up, the formula should contain y in it, because y tells us something about how fast it's moving. All right, what's next? Equation. So the equation you needs to tie the volume to the height, right? Why? Now when we say volume, I'm circling it here in blue intentionally. We are talking about the volume of the water, right? The volume of the water, not the volume of the cup. Volume of the cup is stuck, right? I mean, the cup can only hold so much. But the volume of the water is the thing that's changing, so I want to relate the volume of the water to this height. And what is the formula, look it up, for the volume of a cone?
1/3 pi r.
Yeah, I'm going to write it down. So the formula is volume is 1/3 pi r squared h. That's the formula for, I'm just looking, if you look off your formula sheet, they say if this has a height of h, this has a radius of r, then the formula is 1/3 pi r squared h. I've always found that formula somewhat interesting because if you look at the formula for just a cylinder, this is pi r squared h. So if this is h and this is r, the volume of a cylinder is pi r squared h. What is pi r squared? Area of a circle, right? So what this formula does is it says, hey, take the area of that circle on top and then multiply times how deep it is, and that'll give you the volume. That make sense? It's like a bunch of circles stacked on top of each other. This formula says, hey, Look, you see that cylinder you have over there? If you were to create a cylinder out of this, like this, right? That's solid. The cone part here is 1/3 of that cylinder. It's kind of interesting, right? Because pi r squared h is the same as that formula. So it's a third. Does that make sense? I don't know. My brain is okay with the idea that that cone should be 1/3 of that. Now, in a Cal 2 class, we could show that quite easily. We could show that this is true. All right, so there's my formula, but I've got some issues. First of all, I don't have r in my picture, right? I don't have the radius of this. Now look, this is where we have to be careful. We know the radius of this cup is 3, and that never changes, right? But the water is what we're talking about, and the radius of the water does change. As we move up the cup, the radius changes, doesn't it? So I cannot fix this r to be 3. That would be a big mistake. The other issue is that I'm using h in this formula for the height, right? And in my problem, I used y. So let's just get everything in order first before we do anything. That's the formula out of the book. If I change it to match my situation, I need to change what here to what? Just change the h to y. Okay, so now that formula matches what I have drawn on my page. So there's my equation. If I were to take a derivative right now, it would be very bad. And the reason why is because when I did a derivative, since r is not fixed here, I would get a dr dt out, right? Because of chain rule. A dr dt would pop out. We would also get a dy dt, because we would do a product rule on that. And I don't have any information about dr dt at all. So my only hope at this point is to try and go and get rid of the r. And so I need to do some analysis of my picture here. And what I'm going to do is I'm going to take my general picture. And the reason we show you these problems, like these are like the standard calculus problems, is just to show you the types of things that we can do to get like this r out of here. I can take this cone and I can imagine slicing it right down the middle, just coming through with the little sword and cutting it down the middle. So imagine like that. I'm just going to slice down the middle. And then I'm going to open it up. Okay, I'm going to throw one half away and I'm going to look at it like a cross section. If I do that, what is the picture I will have? It'll be a triangle. Within the triangle, I'm going to have another triangle. That smaller triangle is the water level, isn't it? Like that? Yeah. Then, if I come through here and I slice this down the middle, straight down the middle like that, then I will get, let me do it here. I will get this. Let's throw one of the halves away. I get that, right? Does that look familiar? We did something just like this in the previous problem. Do I know the distance from here to here?
4.
That's 4. Do I know the distance from here to here?
6. 3.
3, right? The distance from here to here is what? You're fixing it, not yet.
Still
Y, and the distance from here to here is r. That's the radius, right? That's the radius of the little thing of water. But more importantly, I have similar triangles. Don't I? That's the key. I have similar triangles. So I'm going to draw this a little bigger. I have a big triangle that looks like this, 4 and 3. I have a smaller triangle that's inside of it, but I'm going to separate the two. This is y and this is r. Right? They both have this 90-degree angle, and this angle are the same, right? Because they came from the same angle down here, both triangles, which means that this final angle must be the same as this one. Yes? similar triangles, which means I can set up the ratio of corresponding sides however I want. So how would you like to set up the ratio of the corresponding sides?
Y over 4 equals R over 3.
You could do y over 4 equals r over 3, right? You could do, I mean, there's a lot. I like that. Let's go with that. Is that okay with you? So this is scratch work still. I'm going to come back to this formula. I have y over 4 equals r over 3. Now, please keep in mind what you're doing here. Are we going to differentiate this? No. We are only trying to get rid of this r, right? So it does not matter how, if we put the variables on top or bottom as much as it did in the last problem. But if I'm going to replace this r, then I need to take this and solve for r, don't I? So let's solve this for r. So just multiply both sides by 3. Yes?
I'm sorry.
No, go ahead.
The y over 4 equals r over 3.
I'm doing similar triangles. So were you here for the similar triangles? You came in a little late, right? Okay, so we talked about it just a second ago. You can take this longer side divided by this longer side must be equal to this shorter side divided by this shorter side. That's the property of similar triangles. If they have the same angles, which they do, then corresponding sides you can set up ratios. Is that okay? So if I solve this, I get 3/4 y equals r. Agreed? And now I can rewrite my equation in terms of just v and y will be the only variables there. Won't they? Are y'all all right? I'm not sure. I'm getting some weird looks.
I guess it's just being able, I know one thing, being able to see how to split, like just knowing how to just split that cone up.
Now you know, right? We in Cal 1 have this imaginary sword that allows us to cut things in half and look at cross sections. This is very useful for spheres also. If you ever have to cut a sphere open. If you cut a sphere open, you're going to see a circle. Right? Okay. In fact, we'll do something like that later on this semester. It's a pretty common technique. So here we go. My equation, I'm going to rewrite it. It's just common sense. Yeah. You're never going to let me live that one down, huh? V equals 1/3 pi, and then r squared, right? So it's 3/4 y squared, but then times y. And that is an equation that has just v and just y in it now. And I'm happy to see that. But I'm going to clean it up before I actually work with it. I'd like to square the 3/4 y. If I square 3/4 y, what do I get? 9/16 y squared. And then times y, which will give me a y cubed. I'm just going to do that on the next line. The 9/3, y'all see that right there? That becomes a 3. So my final version of this is going to be v equals, what? Pi times 3/16. I'm going to write it the other way. I'm going to go 3/16 pi y cubed, right? That's my formula. This is kind of similar to a problem we did last class where we had to connect two variables together, remember? And we did it because we were trying to do volume of a sphere and surface area. Remember that? Yeah. Okay. This is similar to that in the sense that what we've done is we've come up with a final formula that's going to work with the given and what we want. And now we're ready for implicit, right? So here comes the implicit. We're going to differentiate with respect to time. I'm going to differentiate with respect to time, and the derivative of the left side, dv dt, must equal 3/16 pi, all a constant coming along. 3 comes down, y squared. Okay, so we're going to have 3/16 pi, and then the 3 came down, y squared, and then chain rule times dy over dt. Questions here? We take a quick glance at this. dv dt, we know what that is, 2 pi, right? 3/16 pi times 3, that's all constant. Okay, we need to know what y is, right? And we said that how fast things are changing here should depend on y, and it's good, it appears in here. So do we know y in the problem? Yes, it's 3. And dy dt is actually what we're solving for. So we have everything here. So now we're going to solve. All right, dv dt gets replaced with 2 pi. That equals, can I put this 3 and 3 together and make it 9? Okay, 9/16 pi. Y is 3, right? 3? Yeah, squared. And then dy dt is what we're trying to solve for. Three squared is 9. That 9 can multiply across the top and make that 81 over 16, can't it? 9 times 9. So 2 pi equals 81 over 16 pi dy dt. I'm trying to solve for dy dt now, right? The pi's can cancel. Did I mention that last class? Like if you see pi here and pi here, just cancel them. It's like you're dividing by pi on both sides. That makes that quick and easy, just done. That's given. Change in volume, dv dt, this side right here is 2 pi.
Oh, okay, yeah,
The rate at which the volume's changing. And multiply both sides by the reciprocal. So you multiply both sides by 16 over 81. I think you get 32 over 81. Okay?
3 squared.
32 over. Say again?
I'm sorry, there was like a y equals a 3 right in the want, and I'm kind of eyeing it on a 3.
Yeah, it's right here. This y squared. After we took derivative, we replaced it with 3.
What about the 3 right next to it?
Oh, this 3 and this 3 together.
All right, then.
That became this 9 right here.
All right, I'm cool. I'm good.
Good. That's it. I would like to know as a decimal what that is. Just curious. So 32 over 81. About 0.39, about 0.4. This is approximately 0.4. What is that? Unit. We were doing dy dt. Y was the measurement of the height, wasn't it? Height was in feet or inches? It was inches, right? Inches per second. So it's approximately 0.4, I just put feet. Inches per second. What are you solving for? Look, remember how I told you all to do this? You look at this letter right here, right?
Oh, we wanted the
Y.
height. Okay, never mind.
Right? Y is the height of the water at a certain point in time. The height's measured in inches. Time is measured in seconds, so inches per second. Good? All right.
I don't like that chain rule thing.
You don't like this chain rule thing? Oh. It likes you. It has nothing against you. Okay. Let's take a little mental break for just a minute. Just a minute. I was thinking about this a second ago. So, You've learned that the sum of the angles of a triangle has to be what? 180 degrees. You've heard that, yes? All the angles inside a triangle have to add up to be 180 degrees. And that's true for the most part. There are cases when that's not true. And you're probably like, well, why didn't they tell me? Right? And the reason is because this works for flat sheets of paper. If you're on a flat sheet of paper, that's true. This is called Euclidean geometry. In Euclidean geometry, the sum of the angles should be 180. However, not everything is flat. For example, we live on a sphere, right? And so there's a totally different geometry, different set of rules that we have if you're looking on a sheet of a ball instead. It's called spherical geometry. So let's imagine that you had a sphere, like the Earth. And let's say that we start at the North Pole and we start walking straight down to the south, to the equator, right? Then are we going to be in a straight line? No. Okay, it'll be curved, but it'll come down along the curvature of the Earth and I'll reach the equator, right? Then let's say I start walking along the equator for a while. Start walking along the equator and then I stop here. I say, all right, that's enough. I like the cold, I'm going back to the North Pole. I go back to the North Pole and I'm back up there like that, right? Those were all straight lines in the sense of we were walking straight on the curvature of the Earth, yes? That patch right here, if we were to imagine that patch, kind of look at it from a different point of view, this patch that I have here is a triangle on a sphere. That's what we consider to be a triangle on a sphere. And if you look at this angle between here and here, it's kind of hard to show you this because I'm trying to draw on a flat sheet of paper, a three-dimensional thing. Then imagine that the angle between where these two come together would be a 90-degree angle. Because you came from the North Pole, right? You go across the equator, that should be 90 degrees between those two. All right? If you can buy that, please do, because that's the way we define it. We take a tangent line to this curve, a tangent line to this curve, and then we look at the angle between them and it's 90 degrees. When I turn back up to go to the North Pole, what's the angle here? Another 90. And then this angle up here, well, who cares what it is, but I've already violated that rule, haven't I? Because two angles out of the triangle are already 180. And so that third angle is going to make it more. So my point is this. The sum of the angles of a triangle is 180 degrees. That is a true statement if you're on a flat sheet of paper in two-dimensional space using Euclidean geometry. It is not the case if you're in a completely separate geometry called spherical geometry. All right?
Anything else you want to tell us?
Yeah, you're wrong. You're wrong also about parallel lines. Do two parallel lines, like if you're trying to explain to like a young kid, you know, two parallel lines. Let me explain what this is. What would you tell them? Like I'm sitting here like, what's parallel lines? What are two parallel lines? What would you tell me? Lines that what? Never intersect. Anything else? Like railroad tracks? Anything else? I mean, I'm a little kid. I think I get it. Okay, that's fine. That is true. Two parallel lines do not intersect in Euclidean space on a flat sheet of paper. But there are other geometries in which that is not the case. And I'll give you an example. Where are my artists in here? Who likes to draw? No one likes to draw in here? No artists.
Not very well.
You like to draw? Okay, did you ever take any art classes? Do you remember something called a vanishing point?
Yes.
Okay, so look, if I want to draw, let's say I want to draw your railroad tracks, right? If I want to draw railroad tracks from the top, that's what they would look like. It's really bad railroad tracks, but there they are, right? And what we realized quickly, well, not quickly, it took us a long time. What humans realized after a while is that if we want to kind of like be able to look, like what we live in three-dimensional space, so our eyes perceive things one way. If I'm trying to draw something on a flat sheet of paper that's supposed to represent something in three-dimensional space, I have to break some of the rules that go with flat sheets of paper. And one of the most important ones is that this idea of two parallel lines can't hit each other. If I'm going to trick my eyeballs into thinking that it's seeing what I'm really seeing, then what I need to do is this. I need to draw my train tracks, and all parallel lines must go to the same point. So these two parallel lines have to go to the same point, and there it is right there. And then from there I just draw them back like this, and then I can start to put the tracks in. Oops, sorry. Whoa, that's not very good. That's not very good. I'm not there yet. I'm not done. And then let's say that next to the track I had the train station. There's it from the top, right? Now, do you agree that this line's parallel to this line? So those two lines would have to go to this point also, right? And that's the roof of the building. So I'm going to just draw this quick because I've done this before. Okay? So there's my building. See the two parallel lines? See how they go to that point? Do you see the three dimensions? Isn't that a better picture than this picture? That's why caveman drawings suck, okay? Because they had no idea of the mathematics behind what it takes to trick your eye into perceiving it to be three-dimensional.
It's like that street art, the chocolate.
Yeah, that's crazy stuff. They really have to understand geometry to do that stuff right.
They're going to be like, okay.
All right. That's it. That was just a little break from the related rates. Let's get back to them.
I was enjoying the break.
Yeah, I enjoy the breaks too. Unfortunately, I'm supposed to follow a curriculum in this class. It'd be nice if y'all were okay with me just coming here and talking random math all the time, but then we couldn't call it calculus.
As long as we learn that,
As long as you pass that draw the train tracks.
I've asked that question before on test. Two parallel lines, true or false, two parallel lines never intersect. I've asked that as a bonus before. All right, this is a tricky problem. And make this a little bigger so you can see it. A sprinter runs around a circular track which has a radius of 50 meters. Circular track, runner is sprinting around. She runs at a constant rate of 7 meters per second, which I think is really fast. That's pretty fast because the world record for the 100 meters is under 10 seconds, which means it would be about 10 meters per second for a sprint by the fastest man in the world. So I'm not saying because she's a woman. Trust me, I'm not saying that. I am saying 7 meters a second would be fast for Usain Bolt to run consistently around a 50-meter track, a 50-meter diameter or radius track. So my numbers are a little big. Who cares? This is theoretical. This is Superwoman, okay? So she's running around this track, 50-meter radius. Her friend is standing at a point 100 meters from the center of the track. How fast is the distance between the two changing when the two are exactly 120 meters apart? Yeah, this was in the video. So I do have a little bit of clarification here. In my other class, we went through this problem last week, and we were talking about this friend thing. If you're, okay, maybe it's her coach. That I could see the coach watching, you know, like, okay. But if you're just some person watching someone run around a track, I'm not quite sure you're going to fall into the friend status, you know? My friend, way in the, like, stalker status. Regardless, she's got somebody watching her, all right? And what we're interested in is how fast the distance between them is changing. Now, you may be saying to yourself, who cares? This is never going to happen. But one way you could look at this is almost like a crankshaft, and you've got like a piston rod. I don't know if you know how an engine works, but you've got the crankshaft that's turning, right? And what it does is it drives this rod, which goes into a cylinder. I'm drawing the engine sideways, I apologize. Okay, so there's a piston. And that piston's going to move back and forth as the gases expand and get sparked. They blow up and it pushes this piston, down, that pushes this arm down, and that arm pushes this point around this track, around this circle, and then that turns your drive shaft, and the drive shaft goes into your transmission, and then that drives your tires. Okay, so it's turning this straight motion into a circular motion. It's not exactly, but you can see that the geometry in here is somewhat similar to a person on a track running around a person standing on the outside. Kind of, all right? Just trying to get you to see, like, we give you the person running around the track instead of some crazy diagram of an engine or something to start. So everyone kind of understand the question? Any questions on it? I'm going to draw some stuff. Instant in time. And I'm going to move this up or make it smaller. There we go. The instant in time, we have the track. And this track has a radius of 50 meters. The person is where in this picture? Does it matter?
Not really. Well, yes. Kind of.
Yeah, because they have to be 120.
They have to be 120 or 100 meters. That the person, the friend or stalker is standing 100 meters from the center of the track, right? Standing 100 meters from the center of the track.
It doesn't matter where they stand.
Doesn't matter. It can be anywhere on a circle that's around here, right? Anywhere. That's kind of up to me where I want to put them. So I'm just going to pick what is natural to me, and that would be just to put them straight out to the right. I could put them up here. I could put them straight up. I could put them on this side. It doesn't matter which side. I'm just going to decide for myself that they're outside. How do I know they're outside the circle and not inside? Radius is 50 meters. They're standing 100 meters, right? So we know that that distance from there to there, that total distance there is 100 meters. I know that's starting to look a little crammed in there with stuff. In fact, I think I'll move the 50 meters out of here. I'll just put it over here on this side, 50 meters. There we go. All right, this is the instant in time. So what can I draw now?
The runner.
The runner. I need the runner on there. And where should I place that runner? 120 meters away from the stalker.
So like at the bottom.
Well, the distance from here to here is 100, right? So you imagine like swinging up here, like somewhere around here would be 100, wouldn't it? If I just swing this up, it would be around here. Somewhere down here would be 100. So I don't want to put her over here, right? Somewhere on this side.
You want to put her like where the 50.
Okay. It could be here maybe. I mean, I'm guesstimating. There, or she could be down here, couldn't she? She's 120 meters away twice. If she's running, let's say, this way, let's say counterclockwise. Do they run around counterclockwise or clockwise?
Counter.
It's counter, isn't it? Yeah, it is counterclockwise. So running around this way, then she would be 120 meters away here, and as she came back, she'd be 120 meters there, wouldn't she? So at one time she's moving away, at the other time she's moving towards. Understand? But this is the moment in time. I'm going to say this distance from here to here, 120. And I'm just going to keep in mind, in the back of my mind, that there was also a time down here, right, where she was 120. Yeah, we're probably going to we should get two answers. All right. That good for the instant? Okay, how about the general picture? Well, the track's still 50 meters, right? The person's still 100 meters away. But now the person is anywhere, right, on the